So we're transitioning to our final topic. So this is not a continuation of Laplace transforms. This is something different. And we're going to be talking about series, and in particular, series solutions. And so we're going to sort of step back and recall some things we saw in calculus. So if we go way back in the early days of calculus, we said, hey, you know, functions look a lot like their tangent lines. And then we had a whole semester based off that idea. And so I said, okay, well, that's great. Of course, there's always some error. And then Calculus 2 said, you know, we can do better. Because when you think about tangent lines, what you're doing is you're capturing the value of the function, the value of the derivative. Well, what if we use more information? For example, the second derivative. And so you can get what you call a Taylor polynomial. In fact, tangent lines are really Taylor polynomials. They're just like the first order. And then you can get second order. And in some sense, it's a better estimate. You can see here, if you compare, it's a smaller error. See, it's a smaller. And you might say, okay, well, that's great. That's if you use the value of the function, the value of the derivative, the value of the second derivative. Can we get better? And the answer is yes. And Taylor polynomials capture this by saying, well, we're going to get a polynomial that matches locally what the function is doing up to some derivative. And of course, you say, well, why stop at some derivative? Let's be greedy. Let's match all the derivatives. And that's where Taylor series comes from. Where you say, well, the function sum from 0 to infinity, so it's saying all the derivatives, kth derivative at that point, k factorial x minus a to the k. Now, there's a caveat here. There's this word, sometimes. Well, things can happen. It can get dicey. Also, it might happen that, yeah, it matches locally, but only within a certain range. Now, this is centered at x equals a. For our purposes, we're going to focus at x equals 0, or a equals 0. That's what we're going to center around. But basically, what's the idea? So the idea is that we started with a function that we knew. And then we said, okay, here's what the series is. We're going to do something else, but not too far off. We're going to start with something we don't know. Namely, our solution. We don't know the solution to our differential equation. But what we can do is we can say, okay, given that we think of it in this sort of big polynomial, this infinite polynomial, what can we say about what the polynomial looks like? In particular, what are the first few terms? And that can give us a really good estimate. And oftentimes, especially in certain engineering applications, a good estimate is all we need. So that's where we're going. Okay. So a few really simple ideas. We're going to focus on power series, and as I said, power series centered at 0. And you should think of it as this big infinite polynomial. So we denote this, there's some notation here, capital letter sigma, sigma for sum. So we're adding up. You have this k, and k is an index. And it just says k ranges. And it's where you start, and we start here at 0, and where you end. And oftentimes we'll care about infinity in theory. In practice, we'll be happy if we say, well, what's the first 10 terms? And we have c sub k, x to the k. So the coefficient depends on which coefficient we're looking at. That's why there's a c sub k. It depends on where we're at. So this is a shorthand way of saying c0 plus c1x plus c2x squared plus ... And whenever you see ... really this is shorthand for saying the pattern continues. That's what ... means. The pattern continues. When does it make sense? Well, that's when it comes down to questions of convergence. And something converges if the partial sum, so in other words, up to some n value converges. Now, we're not going to worry too much about convergence questions. In general, we'll do a little bit about what we call radius of convergence. But there is an important idea here And we should spend a little bit of time explicitly saying this sentence here. Because it seems so obvious and not so important. But it is an important idea. It says, if I have two series, then they're equal if and only if all their coefficients are equal. And think of it in terms of polynomials. Two polynomials are the same if all the coefficients match. And this is an idea that we've actually used. If you think about partial fraction decompositions, it's all based on that idea. I have two polynomials, and I just have to choose the coefficients the right way so that everything matches up. So if we do have two series which are equal, we're going to set their coefficients equal to each other. And we'll see how that comes up in a few minutes. All right, well, let's do a little recall from Calc 2 of things that we know. So from Calc 2, there are known power series. Now, I am not anticipating that we're going to expect you to memorize these, but this is just for your information. Things are known. There's a few that I highly like. There's e to the x. That's a great one. That's sum of x to k over k factorial. And you can get a lot of nice information out of that. In fact, once you have e to the x, the following four actually follow pretty quick once you have the right interpretations in place. 1 over 1 minus x. This is another famous series. This is called the geometric series. And oftentimes when you hear the word geometric, especially in a math context, geometric means multiplication. So the idea is you're multiplying the previous term by some amount. So it's like x, x squared, x cubed, so forth and so on. And this is true as long as x is small. So this is a case where there are limitations to when something is true. We'll see examples of this at some point in the next few sessions. This last one, 1 plus x to the power alpha. Now, if you've taken an algebra class, which I hope you have at some point, you probably have encountered expressions like this. 1 plus x squared. All right, it's 1 plus 2x plus x squared. Great. You might even know 1 plus x cubed. 1 plus 3x plus 3x squared plus x cubed. And you say, okay, great. But what if you had something weird? 1 plus x to the pi. Wait, what? Can you do that? Is that allowed? And the answer is yes. So this is a binomial sum. And you get these, what you might call binomial coefficients. And, well, okay, how do you actually compute these? Well, it turns out they're a lot simpler to compute than you might think. So let me quickly tell you how to compute them. And just because I think it's an interesting thing. It's a ratio of two things. So downstairs it's k times k minus 1 times k minus 2. And you keep going until you get down to 1. Now if you saw that, k times k minus 1 times k minus 2 all the way down to 1, what would you think? K factorial, yeah. That's exactly what you should think. Now the upstairs, you do something really, really similar. Except in starting in here, you have k, you start alpha. Alpha. Alpha minus 1. Alpha minus 2. And you keep going, not down to 1, but you keep going until you get k terms upstairs. So there are k terms multiplying downstairs. There's k terms multiplying upstairs. The only difference is, where do you start? One downstairs starts at k, goes down to 1. Upstairs starts at alpha and goes till you have k terms. Okay, so those are known power series. But as I said, we're sort of dealing with the unknown. And what we need to do is get comfortable with doing certain operations. And so the real important part of this slide, I would say, are these first, 4 bullet points. If you can do these first 4 bullet points, you're going to be in pretty good shape. Ideally, you should be able to do more than that, but let's start with that. So the first thing says scaling and adding. So suppose we have two power series and want to combine. So A times the first, B times the second. And what do we do? Well, first off, what if we just have A times this series? What should we be able to do with the A? Distribute, okay. So you can think about, we can take that and we can move it inside. In other words, you can put constants into your series. The other thing is, suppose I want to add. Well, think about polynomials. If you're ever in doubt, think about what would I do if this were a polynomial? If I have two polynomials and I want to add them, what do I do? Add what?
Like terms.
Add like terms. When is a term a like term? Yeah, you look at things which have the same power, you add their coefficients together. That's what you do here. You say, okay, here I have x to the same power, that's called x to the k. And I say the coefficient of the first is this capital A times A sub k. The coefficient of the second is capital B times B sub k. Add them together. So in other words, it's the intuitive thing, what you should expect to do. Now there's a couple of things that you have to be a little bit aware of. And notice here, we both start at the same place. What if we didn't start at the same place? What can we do? Well, that's the second bullet point. If you want, you can always pull off some terms at the start. So what's going on? Well, this sum says, what is it? You start at m and go to infinity. So the first would be c sub m x to the m. Next would be c sub m plus 1 x to the m plus 1, and so forth and so on, all the way to infinity. What we can do is just say, look, I'll pull off to a certain point, and I'll put everything else. See, this would be a dot, dot, dot here. I'll put everything else into a new sum that starts at n. So I can pull off the first few terms. Now, how many can I pull off? And the answer is I can pull off as many as I want. So how many do I pull off? Well, I pull off enough so that I can work with what's left in a nice way. So as an example, if I make these indices the same, so I can add them together. So that's what I would do. Yes?
This is implied, but could you put all of the regular polynomials on the other side so you could get at k equals n, you could find k equals m by taking k equals m minus all of those terms in between them?
Oh, well, sure. You could do a subtraction, and then you could take a difference of these two sums, and you can get the terms there are what's left. You can do all sorts of fun things. The next bullet point, this one is good. I like this one. It says, shifting the index of power series. Now, remember, this index is what we have here, this k. K is not really part of the answer. It's just a convenient way we index what's going on. And we can change the index. And the thing you should think about is substitution. So if you go back, you think Calc 1. We had this really beautiful idea for doing integration, where we said, well, let's just do substitution. We say things like, oh, u equals x squared or something. But in essence, what is substitution about? What's the idea? The key idea about substitution is changing the name. That's what it is. That's almost all it is. And once you understand that, you say, oh, okay. So here, what we can do is we can change the name. So it's like, well, I want to change this exponent to something more convenient. So instead of k minus I just want it to be just the index. I don't want the minus I there. So I say, okay, no problem. We'll come up with a new index. We'll call that new index L. And L is set to be k minus I. Now, if L equals k minus I, well, that's the same as saying k equals L plus I. And what do? Well, we make sure everything gets changed. So k minus I becomes L, so that's why x to k minus I becomes x to the L. But we have to change everything. So where did we start? Well, we used to start at k equals m. If k equals m, what does L equal? M minus I, because I can take this relationship, L equals k minus I, and I put k equals m. This infinity says I go up till I hit infinity. So this is really, oftentimes we don't write this, but there's this upstairs part that says k equals infinity. That's where we're going to. So where do we go to now? Well, infinity minus I, also known as infinity. Yeah. And how about our subscript? Well, C sub k, replace k by L plus I, becomes C of L plus I. So this is shifting the index. It's just saying, hey, let's just change the name to make things more convenient. This is a really powerful idea. And the last, sort of most important bullet point that we need to talk about is how do you take derivatives? So what's the, intuitively, what should you do? If I have a derivative of a big polynomial, how do I take the derivative of a big polynomial? Term by term, every individual term. That's what we're saying here. If you want to take the derivative of a polynomial, think about taking the derivative of each piece. Well, in other words, pass the derivative through the sum. C sub k is a constant. And you say, okay, what's the derivative of x to the k? Well, what is the derivative of x to the k? K comes down, x to the power k minus 1. All right. The last thing, which hopefully we won't have to do too often, is multiplying series together. And that says, okay, suppose you have one series, you want to multiply it by another series, what's the result? So keep in mind, what does this mean? Well, so this is really shorthand notation. We're saying we have a0, a1x, a2x squared, a3x cubed, and so forth. That's that part. And then on the other hand, we have this other piece that's saying, all right, we have b0, b1x, b2x squared, b3x cubed, and so forth. So that's what these things are. Now, if you saw this, what technique would you think of? FOIL. Right. Now, you might say FOIL, that stands for first, outer, inner, last. But what does FOIL really tell us to do? What's the principle behind foiling? Now it says pick a term from the first, pick a term from the second, and you multiply them together. But then you do that in all possible ways. That's what foiling is. All possible ways. And all right, well, great. So how do we do it? Well, imagine here's my first sum. All right. And then here's my second. And we want to multiply them together. So what we'll do is we'll actually flip this one around. We can do that. So instead of saying dot, dot, dot at the end, we'll say dot, dot, dot at the beginning. And now we'll say, okay, suppose I just want a constant. Well, the only way I can get a constant multiplying these two together is to multiply the constants together. So it's a0, b0. What if I want to get x out? How can I get something involving just x to the 1, multiplying these two together? Well, a0, b1x, and a1x, b0. So a0, b1 plus a1, b0. How about x squared? a0, b2x squared, a1x, b1x, a2x squared, b0. So there's the a0, b2, a1, b1, a2, b0. X cubed, we can do that too. a0, b3x cubed, a1x, b2x squared, a2x squared, b1x, a3x cubed, b0. You'll notice what's happening. Well, you have the a subscripts are going up and the b subscripts are going down. So that's what's happening, and what we have is convolution. So the a subscript's going up, b subscript's going down, and that's the answer. And you can, of course, keep doing that as often as you like. Okay, so that's the principle at play. Now, in practice, I don't think we'll actually have to deal with that particular operation too much. Is it possible to divide series? The answer is yes, but don't do it unless you've had something to drink. Well, or at least a really good root beer or something. You know, be smart, don't start. So, in practice, we'll only need a few basic ideas. So let's start with an example. Rewrite the following as a single power series. Now, let's not worry about where this came from. It's just some expression. We have this, and we want to rewrite it as one power series. One power series to bring it all together. Sum k equals 1 to infinity, k times k minus 1, c sub k, well, we don't know what c sub k is, but it's something, x to the power k minus 2, and the sum k equals 0 to infinity, c sub k, x to the power k plus 1. All right. Now, there's some issues here. These exponents don't match. And so you really want to make sure the exponents match before you start adding coefficients. There's other issues. The starting points don't match. So it's not just as simple as like, oh, we just put them together and life is good. We gotta fix some things. Now, what should we fix first? The exponents not matching or the starting points not matching? So it makes more sense to do the exponents first. Now, the reason I say it makes more sense to do the exponents first is when you change the exponents, what happens to your starting points? They change as well. So if you change your exponents first, then you only have to change the starting point once. Okay, so let's do this one first. So currently our index is k. We're going to come up with a new index. Do you have a favorite letter you like to use? W. W? Wow. That's a bold move, W. Should we be bold? No? I will say traditional indexes are I, J, K, L, M, N. That tends to be the range. Math is weird. It has like certain ranges of the alphabet that are certain things. So sort of the I through N range is indexes. A, B, C, those are your constants. F, G, H, those are your functions. X, Y, Z, W, those are your locations. Y, I don't know. They just chose it. How about we do L? L should be pretty simple. So we want to make this x to the L power. All right. So if I want to go from x to the power k minus 2 to x to the L, what's the relationship between k and L? Yeah, L equals k minus 2. It's nothing profound. Just say, what's the obvious thing? L equals k minus 2. All right, that's great. So another way to write this is k equals L plus 2. All right, if k equals 2, that's where we're starting before, where's our new start? Zero, because I can put k equals 2. 2 minus 2 is 0. Previously I went to infinity. Now we go to infinity. K, okay, is L plus 2. K minus 1 is what? L plus 1. You can think of it as L plus 2 minus 1. C sub k will be what? C L plus 2. Okay, so that's the first sum. All right, now we're ready for our second sum. Okay, so again, we want x to the L. So what's the relationship between k and L on this sum? L equals k plus 1. So we're not trying to be creative here, because creativity is great in some places, but here it's just sort of like, well, let's just make things simple. Now you might say, well, wait a second, Steve, I thought you said L equals k minus 2. Yeah, in this sum. That's fine. But we're in a different sum now. So it's okay to use L to represent something different. And you might say, well, can't we use a different symbol? Well, yeah, but if you make them both x to the L, it's much easier to see how things sort of fit together without having to think too hard. Our goal is to not think too hard. We want to think the right amount. Of course, if L equals k plus 1, k equals L minus 1. All right, where do we start? Start at 1, because 0, k equals 0 becomes L equals 1. Where do we end? Infinity. What's our subscript? Sorry, what's our piece that goes here? C sub L minus 1. Okay, great. So now, these match. That's wonderful news for us. The starting points don't match. That's not good news for us. So what do we do here? Okay, so I should take off the 0 term from the first one. I just need to go far enough so that they both agree. So this one says start at 1 and keep going. This one starts at 0 and keep going. So if we say, okay, if we pull off the 0 term from the first one, so what happens when we plug the 0 term in? What do we end up with? 2 times 1 times C2, and x to the 0 is 1. Okay, then we pull off the first term. Then we have the remaining terms, 1 to infinity. But it's still the same sum. The only thing we've done is pull off the first term. So it's still L plus 2, L plus 1, C L plus 2, x to the L. All right, and then, because I ran out of space, there's the other one, 1 to infinity, C L minus 1, x to the L. So we're almost there. What's the last thing for us to finish? Well, simplify by? Yeah, we combine. Our starts agree. Our powers of x agree. Life is good. We still have this 2c2 at the front. That's no problem. Oftentimes, the start has a little bit of noise. That's not too surprising to us. And that won't bother us. Then we start sum from 1 to infinity. And we just add the coefficients. So it's L plus 2 times L plus 1, C L plus 2, plus C L minus 1, x to the L. And there we go. There we go. Is there a question?
Are these constants independent here?
The C's?
Yeah.
As of right now, they are. Whoa. It's a weird way to say that, Steve. Yes, it is a weird way to say that. Because in essence, this is not equal to anything. So there's no constraint. And so they're just, right now, these are just operations we're doing. So yeah, so these constants, as this problem is given, are independent. Of course, you might say, is there a different way we could give such a problem? Oh, that would be interesting. But surely, I doubt that we'll come back.
Yeah, I'm glad we don't have to deal with that.
So, let's do a different problem. Let's get back to doing differential equations. So let's suppose that we have y, and we're going to think of y as this series. Sum k equals 0 to infinity, c k x to k. Because, the philosophy is that we can approximate functions by these power series. And so it's reasonable to say, okay, let's just say, here's our function. What we don't know is we don't know what the constants are, these c sub k. But we're told it's a solution to this differential equation, y double prime plus xy equals 0. Now, if you saw y double prime plus xy equals 0 on a test, what would you normally do? Well, separation would work if it was y prime. This is y double prime. So probably the best thing to do on a test would be, I'll skip the question and use my time wisely on the rest of it, because we don't really have good techniques for this one. So there are differential equations where the techniques we have, even if it's not a very hard differential equation to write, are not going to help us get very far. Okay, so we don't have a good way to solve that differential equation yet. Okay, but okay, we're told that y is a solution. And then we're also told that y of 0 equals a box. Oh wait, I think that means we get to fill a number in. What would you like y of 0 to be? 6. And y prime of 0 is 7. That's the first number I heard. All right. So we have this solution. We have some initial conditions. And we're told to determine C0, C1, all the way up to C8. So in other words, we're trying to get some sense of what's this solution look like. And you can get a good sense of what a solution looks like by saying, well, what are the first few coefficients? Because locally, that's how the solution will behave. All right, well, how to start? The good news is we know what y looks like. We say, all right, here's our function for y. I'll just copy it again. Y is the sum k equals 0 to infinity, ck x to k. Now, keep in mind, what does this mean? It means really our solution looks like C0 plus C1x, C2x squared, and so forth and so on. So what can we say about y of 0? What happens when we plug 0 into this sum? Most of it is going to be 0. Most of it is what's not going to be 0. The C0 term. Now, we could even see it from this expression here. You say, okay, look, 0 to a power is 0 as long as our power is at least 1. 0 to the 0, we sort of say, well, that's a different story. So, wait, we know why 0 is. Ha-ha! We've already made progress. We're already 1/9 of the way through. Yes! Okay. What about y prime? Well, what is y prime? Let's write it as this sum. So what's the derivative here? All right, the k comes down, ck x to the power k minus 1. Now, if you were to write this, it would look like the first term would be, normally see how we start at k equals 0? If I put k equals 0 here, what comes out when you have k equals 0? You get 0 automatically. So what we can do is we can actually change, instead of starting at 0, we can start at 1. Okay, so what does that look like? Well, it looks like C1, 2C2x, 3C3x squared, so forth and so on. So that's what this looks like. So what is y prime of 0? C1. And it's also 7. Wow! We've gotten 2 parts of our answer. So we've got the C0, we've gotten the C1. Now it's just this part that remains. So in essence, when they give you initial conditions in terms of the series solutions, it's basically saying, how does your series start? Okay. I suspect the next few terms are going to be the more interesting ones. Well, let's keep this going. Let's focus on y double prime. What is y double prime? Well, we have y prime. So what does y double prime look like? K minus 1, ck x to the power k minus 2. And where should we start? Yeah, we can start at 2. Now, you might say, do you have to start at 2? No. You could start at 0, you could start at 1, but 0 and 1 are automatically 0, so they're not interesting. So in essence, it says, 2 seems to be like the natural place to start, because that's the place where things actually have a chance of having something happen. Okay, so that's y double prime. What's x times y? Well, that's x times the sum k equals 0 to infinity of ck x to the k. I'm just writing down x times y. What can we do with the x that you see here? We can bring it in. So this can be rewritten as the sum, 0 to infinity, ck x to the k plus 1. All right. So let's put these two things together. Namely, y double prime plus xy, that's the sum, k equals 2 to infinity, k times k minus 1, c sub k, x to the power k minus 2. So that's the y double prime, just copying it down, plus the sum, k equals 0 to infinity, c sub k, x to the power k plus 1. And all of this will be equal to 0. Now, it would be nice, it would be really nice if we knew how to deal with that sum. Is there anything we can do with that? Yes?
We already know that because k equals 0 and k equals 1, the first summation here equals 0, so k equals 2 is the same as k equals 0. Can we do it like that?
Well, we can. I will say, do you notice anything about this particular expression? Oh, it's this one. Yes, yes. Oh, it's like it was planned. It was planned. It was definitely planned. Okay, so this expression here, we can say, hey, this says 2c2 plus the sum, L equals 1 to infinity of L plus 2, L plus 1, C, L plus 2. My L's look really strange sometimes. Plus C, L minus 1 times X sub L equals 0. Now, I just want to say it equals 0. What's another way we could write 0? Just to really emphasize the zeroness of it. Just how 0 is your 0. Well, another way to write 0 is the sum 0 to infinity of 0 times, I should use L. X to the L. You can't get more 0 than that. Okay. They might say, weren't we already sufficiently 0, Steve? Yes, but I want to be even more 0. Extra 0. 0 plus plus. Now, our great moment. There's a statement. I said it was a really important statement back at the very beginning from the day. This statement right here. Two series are equal if and only if their coefficients are equal. I have an equal sign. These two things have to be equal to each other. So, our conclusion. What does that say about this 2c sub 2, the constant on the left-hand side? This has to equal 0, because the constant on the right-hand side is 0. What about the coefficient of x to the power L? It also has to equal 0, because when I have something as 0 on this side, that just means all the coefficients are 0. So that says, oh, there's lots of zeros going on here. Now, previously we already knew C0 was 6. We also knew C1 was 7. What can we say about C2? C2 equals 0. All right, so progress is being made. Progress is being made. All right, so let's recap. So we know that C0 equals 6, C1 equals 7, C2 equals 0. And we just have to find a bunch more stuff. Okay. That's no problem. 6 more to find. So I'm just copying C0 equals 6, C1 equals 7, C2 equals 0. And we have this. So what does that say? So I'm going to copy this down as well. This says for L greater than or equal to 1. The reason I say starting at 1 is that's where the sum starts, L equals 1. We have L plus 2 times L plus 1, CL plus 2 plus CL minus 1 equals 0. Okay. So this is going to help us fill in the rest. Because what we have here is relationships between the coefficients. So we're saying the coefficients are not completely independent of each other. If I know some coefficients, it forces other coefficients. And so we say, okay, given that that's the case, what we can do is figure out, well, let's find a way to, there's a fancy word for this. There's something called a recurrence relationship, which says, all right, I want to rewrite a coefficient in terms of earlier coefficients. So that's the goal. We want to get a recurrence relationship going here. Now, this is not the best way to write it. And ideally, you should say, you want to have something written in terms of smaller coefficients. So because this is the larger subscript, that says we want to solve for that one. So we want to have the larger subscript in terms of smaller subscripts. So if we just rewrite, you would get the following, namely CL plus 2 is minus CL minus 1 divided by L plus 2, L plus 1. The only other thing I would do here is I don't really like the L plus 2. So let's just change it. And how do you change? Well, you change your index. You're allowed to change your index. So let's call L plus 2, let's just call it n. Just like we did with sums. So C sub n. So if L plus 2 equals n, another way to write this is that L equals n minus 2. What does C sub L minus 1 become? N minus 3. So this says 3 terms back. So if I want to know this term, I go 3 terms back, n minus 3. Divide by, L plus 2 becomes n, L plus 1 is n minus 1. So, and this is for n starting where? Previously we started at 1. So if L was 1, n was 3. So now this says, hey, starting at n equals 3, I can figure out my coefficient by going 3 steps back. So if I want to know C3, well, according to the rule, C3 is minus C0, because I go 3 back, divide by 3 times 2. So what does that simplify to? What? Negative 1. Because C0 is 6. Minus 6 over 6. C4, that's n equals 4. Plug it in. Minus C1 over 4 times 3. All right. Well, what's C1? 7. So C4 is negative 7 over 12. How about C5? C2 over 5 times 4, but C2 is 0, 0. C6, so that's minus C3 over 6 times 5, which gives us 1 over 30. C7, okay, that's minus C4, just plug it in here, n equals 7, over 7 times 6, 1 over 72. The 7's actually cancel. And 6 times 12 is 72. C8, probably you can tell me that before I can finish writing it down. 0, because you go 3 back. In fact, once you see 0, you're always going to get 0 every 3 terms. And so, if we want to, we now have a really good approximation for the solution to y double prime plus x, y equals 0, y of 0 equals 6, y prime of 0 equals 7. Namely, it's 6 plus 7 times x, 0x squared, minus x cubed, minus 7/12 x to the 4th, 0x to the 5th, 1 over 30 is x to the 6th, 1 over 72x to the 7th, so forth and so on. So we can solve. Or at the very least, we can get really good approximations. So there's a general strategy that comes into play. And here's the general strategy. So if we're after finding power series solutions, say, okay, let's say our answer is a power series. Sum k equals 0 to infinity, c sub k, x to the k. All right, great. Now, well, we differentiate as needed. So usually we need the first derivative or the second derivative. You can, of course, keep going. In practice, we'll be satisfied if you get to the second derivative. Then once you have that, you substitute the y prime, y double prime, any other series that show up, so that what you have is really, you should say, I'm making everything into this big, big polynomial. And once everything's a big polynomial, you clean it up. The cleanup is put it all into one single expression. So change your indices, change your exponents by reindexing, do whatever it takes to get everything nice and neat. And then you say, okay, the differential equation, you have something equals something, and you compare coefficients to determine relationships. And when we talk about relationships, really, you'll get a recurrence relationship going. It says, how does the constants, how do they depend on each other? Now, in some cases, it's possible to get a general solution. In many cases, we we can compute the first however many terms we need. So let's just quickly sketch an idea here. Y prime equals 3y. Now, if you saw y prime equals 3y, what would you say the answer is? Do you remember? Hopefully you can solve this one. Maybe even in your head.
E to the 3t.
Okay, so it's some constant e to the 3x, where it's, it depends on the initial conditions. Or e to the 3t, right. It just depends on whether you use x or t. So the idea for a power series would say, well, look, I know what y prime is. That's the sum k equals 0 to infinity k ck x to k minus 1. And I'm going to set it equal to 3y. K equals 0 to infinity ck x to k. Y prime equals 3y. Now, we'll do some really simple things. We'll say, well, I don't need to start at 0. I can start at 1. Because when I have k equals 0, I get 0 automatically. So I'll just change my subscript where I start. And now do a shift. So this becomes sum L equals 0 to infinity. And I'm going to have x to the L. And let's see. So that says k equals L plus 1. So L plus 1, C L plus 1. And on the other side, push the 3 in. So sum L equals 0 to infinity, 3 C sub L x to the L power. I just changed the k to L just so that things match up nicely. And now we're like, hey, wow, check this out. What's true? Well, things have to match. So in particular, you come up with the observation that L plus 1 times C L plus 1 equals 3 CL. This is true for L greater than or equal to 0. Or you get the recurrence relation C sub L plus 1 equals 3 over L plus 1 C sub L. Now, we're out of time, but I will say if you start with this and you keep this going, you discover that C sub n will look like the following: 3 to the power n C0 over n factorial. And if you were to plug that series in, so you had the sum k equals 0 to infinity, C0, 3 to the n, n factorial x to the n. So I'm just replacing c k with the right expression here. Oops, start with n. Well, the C0 is a constant. Pull it out. And what do you have? You have 3x to the power n over n factorial. And for all you great lovers of power series out there, do you recognize that power series? It's e to the 3x. So, yeah, see? Isn't this so much harder? Wait, no. It's different. It's different. Okay. Well, to be continued. To be continued. Have a good day.